In section 2.5, we're going to look at some applications of matrices. Really, we're going to look at one application, and that's stochastic matrices. Stochastic matrices are good for modeling things where you have people or other populations that are moving between various states. And I don't mean states necessarily like, Georgia, but different just sort of abstract states. And I've got an example here that I want to start with. This graph, and this is an oversimplified model, but it says this graph and matrix represent people in a group who drink Coke, Pepsi, or neither each day. And the model is kind of simplified because we're assuming that it's always the same people. We don't get any new people coming or going from the group or anything like that. But what this says, these are the people who are drinking Coke, Pepsi, and neither. And what this says is if somebody drinks Coke on one day, then the following day, there's an 80% chance that they'll still drink Coke the next day. There's a 10% chance that they'll switch to Pepsi, and a 10% chance that they'll switch to drinking neither. And the people drinking Pepsi, there's a 70% chance that they'll drink Pepsi the following day. There's a 10% chance they'll drink water, and a 20% chance they'll drink Coke. So if you think about what's going on here, you've got people, in here. Say you had 100 people in here one day, then you're going to have 10 of them going over here, 10 of them going down here, and 80 of them staying in there. On average, this is probabilities. And the matrix over here is another way that we can encode the same information. So up here, this is where they're coming from, and this is where they're going to. So people with Coke, 80% probability for each one of them to drink Coke the next day. To go from Coke to Pepsi, that's going to be here. From Coke to neither is going to be here. And you can think of this in a couple of different ways. You can think of this as being the proportion of people who go from Coke back to Coke. You could also think of it as a probability of an individual who's drinking Coke, the probability that they will switch to, or that they'll stay with Coke the following day. And same thing for the other numbers here. So a few things about these probabilities. Probabilities have to be between 0 and 1. A lot of the time you think of probabilities in terms of percent, but in math usually you drop the percent, you just use it as a fraction between 0 and 1, or a decimal. And another thing is, we're not losing any people. So right here, the Coke drinkers, notice 80%, 10%, and 10%. We have to account for all of them. What that means is the probabilities on the arrows coming out of any state has to sum up to 1. And if you look at what that means in terms of the matrix, it means that the columns have to sum to 1. And the matrix of probabilities that we have here is called a stochastic matrix. So let's look at how to use this. Suppose that on day 1, 50% of the people drink Coke, 50% drink Pepsi, and nobody drinks neither. So we can represent this with the matrix or column vector here, this 0.5, 0.5, 0. Now these are in the same order as we have up here, Coke, Pepsi, neither, Coke, Pepsi, neither. So this is Coke, Pepsi, and neither. If we want to determine the distribution for the second day, what we do is do x2 times px1. And let's do that with Octave, and then maybe we'll talk about it as well. So here in Octave, I've already got this matrix typed in. So here we go. And if we want to determine the distribution for the following day, this matrix I'm calling P, and our x1 was 0.5, 0.5, 0. If I do P times x1, that tells me what's going on the following day. We will have 50% of people drinking Coke, 40% drinking Pepsi, and 10% drinking neither. let's go back and look at how matrix multiplication gives this to us. I'm going to copy the matrix down here and at least do part of the multiplication. Let's see, what do we have? 0.811. Then 271433. Okay, when you take that and you multiply it by 0.50, notice what we've got here. So 3 by 3 times a 3 by 1. And so that's going to give us a 3 by 1 for our answer, or our product. And this the top number is going to come from this times this. So let's see, that's 0.8 times 0.5 plus 0.2 times 0.5 plus 0.4 times 0. And when you add all that up, it gives you 0.5. Now, what that's telling you here really is 80% of the, well, 50% of the people are drinking Coke. 80% of them will drink Coke the next day. 50% of the people are drinking Pepsi. 20% of those will drink Coke the next day. So that's how you add this up and you get this. Now, I did this example with a 0.50. If you had actual numbers here instead of percentages, that would work too. Let me show you what I mean. Suppose instead of this, we had the actual numbers of people. Let's say that, I need to erase this too. Let's say that we had 40 people drinking Coke, 40 people drinking Pepsi, and also, well, 0 people drinking neither. If you take that and multiply it out, this will give you the same thing, but instead of giving you percentages, it'll give you raw numbers. This will give you 0.8 times 40 plus 0.2 times 40 plus 0.3 times 0. So that gives you 40 people. Yeah, 3.2 and 32 and 8. So yeah, 40. And we could do the same thing to get the other numbers there. We could also use octave to give that to us. But I know the book does some examples like this where they have raw numbers there instead of percentages. But I want to stick with percentages for a little bit. So let's go back to this. I had 0.50, and that gave us 0.40. I'm going to erase this and just put this in here. .5, 0.4, 0.1. I misspoke a second ago. Okay, so this right here is what I call x2, the distribution on the second day. If you want to determine this for later days, you can just keep multiplying by p. So if I wanted to find x3 would be p times x2, or you can think of it as p squared times x1. So let's look at that on octave. So over here on octave, let's see, my x1 was this, so if I do p times x1, I get that. So that's my x2. If I do p squared times that, it gives me x3. So this will be on the 4th day, 5th day, 6th day, 7th day. And notice something interesting. This seems to be converging to a certain number. Let's raise this to a big number. Let's say to the 100th. So this would be, I guess, after 101 days. Things are rounding off there. If I change this to format rational, and I do that, we get 9/16, 5/16, 1/8. What that means is, at that point, it's not changing anymore. If I do p to the 101, notice it's the same thing. So what's happening here is we're achieving what's called a steady state. The steady state is what happens when you have the solution of x equals px. And there are a couple of different ways you can do that. You can find the steady state. You can either do what we essentially did a second ago, take the value of p to the n times x as n grows large, or you could solve this system right here. And we'll do that in an example in a few minutes. But anyway, this is a good way to do this. Let me show you a couple other things. Over here, we had x1 for our original, the distribution on day 1. If I raise this to a big number and multiply by x1, that gives me the distribution, in this case, after 101 days, when it's settled to a steady state. If I just take the matrix P and raise it to the 100th power, an interesting thing happens here. Notice all those vectors, each one of those columns in the matrix converges to that steady state. And that's sort of interesting. The main thing we're going to be doing in here is starting off with a certain probability or a certain distribution, and then seeing what happens to it over the next few days and over the long term. One more thing I want to do before we end this video. Suppose x1 was something different. Suppose we started off with nobody drinking Coke or Pepsi. That would be like this, 0, 0, 1. So 100% of people are in that third category. And let's see, I'm going to write this down. Our steady state, sometimes I tend to call it SSV for steady state vector. But what was it? It was 9/16, 5/16, and 1/8. All right, so if everybody's drinking water, they're drinking neither Coke or Pepsi on the first day, on the second day, we get this distribution. A lot of people switch to drinking Coke. Well, 2/10, 2/5. Let's see, you got 40% drinking Coke and 30% drinking Pepsi and 30% still drinking water. If I go after 2 days, 50% are drinking Coke, and then it's going to trend upward. And after, say, 10 days, we're here. After 20 days, and notice what this is. This is the steady state. So it achieved the same steady state from starting from a different starting state, or a different starting distribution. That's a better way of saying it. So anyway, that'll happen with these things. If the matrix, or if the process is what's called regular, then regardless of where you start, you'll always end up in the same place. We will talk about that probably more in a later chapter, but for now you can count on all the examples we do as working out like that.